Today we're looking at lesson 2.1, which is on inductive reasoning and conjecture. And this lesson has quite a bit of vocabulary that may or may not be new for you, but in order to understand the lesson better, you do want to understand the words that we're using. So a conjecture and the type of reasoning that we're using is basically assuming if you see a pattern, that pattern is going to continue. And that's called inductive reasoning. And then if you make a statement about that pattern, that would be called a conjecture. So that's what I had here, a statement that's reached using inductive reasoning, or a statement that you have about the observed pattern, that's called a conjecture. So it's going to ask us here to write a conjecture that describes the pattern in each sequence, and you'll see sequences on the next slide. So then use your conjecture to find the next term in the sequence, or the next item in the sequence. So this is talking about follow-up visits, maybe to a doctor or something, and the pattern that we're looking for is going to help us make a conjecture, and it's also going to help us find the next item. So if we think about the pattern between December, then May, then October, then March, that would be more like if you think December and then you're thinking, okay, it's the 5th month after is May, and then the 5th month after that is October, and then the 5th month after that is March. So what would be the 5th month after August? That would be April, May, June, July. Well, after August, I just told you the answer. What would be the 5th month after March? And it would end up being August. So that would be the next item on this sequence. And my conjecture that I would make is that the next month is going to be the 5th month after the preceding month, or the one that you just had. So you'd write that statement as well. Now we're looking at just numbers here, and we need to think of the pattern and write that pattern down. So it looks like each time you go from 10 to 4, then 4 to -2, and so on, that you're subtracting 6. So your conjecture would be subtracting 6, and then we would subtract 6 from -8 to get our next term, which would be -14. So you would put as a conjecture that you have to subtract 6, or put your conjecture as the pattern that you found, and then put the next item. Then there's one more. These 3 triangles, so we need to draw the next triangle that will happen based on the pattern, and as you can see, your conjecture, it looks like, is going to be that each triangle, or each shaded triangle in the previous figure, it's divided into 4 other equilateral triangles, and you basically start by drawing your triangle from the middle, in the middle of each side. So if you see here, from this to this, that's what I'm talking about. So then if you take each shaded area, then you do it again and draw a triangle in the middle of each side, or at least with the vertices in the middle of each side, then you're going to keep getting more. So your last triangle, or your next triangle, you're going to have the one that you started with, the middle one, and then each of these in the 3rd section, and then you go to each shaded area after that. So this is, all this part is shaded, shaded, shaded. This is shaded, 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 and shaded, shaded, and shaded. So around each triangle, there's basically 3 triangles that are shaded, and you would just draw more triangles in each one of those spots and shade it. So it would look like, let me draw your triangle. It would look like do it a different color. these are all your new triangles that you're adding on in each shaded area. And that would be your next triangle. Your conjecture would be that in each shaded triangle, you're going to divide it into 4 more equilateral triangles by drawing another white triangle in the middle, like we did. I did mine pink just to show you the difference between this one and this one. All right, here we're going to make some more conjectures, making a conjecture now about each value, or if it's a geometric relationship, about their relationship. And then we're either going to list or draw some examples that support the conjecture that I made. So if we think of the sum of 2 even numbers, what could we always have when you are adding 2 even numbers? Is your answer always going to be even, or is it going to be odd? And you can try it out too, but think of the numbers 2 and 4. If you add those together, what are you going to get? 6. Then if you keep going, 4 and 6, what are you going to get? 10. And as you can see, based on the pattern, what you'll see is that everything that's added together, 2 even numbers, is always an even number. So my conjecture is the sum of 2 even numbers is even. And you can just give one example like we did. 2 plus 4 equals 6. And that would be your example or your support for your conjecture. Next one, also talking about numbers. So this one says the sum of the squares of 2 consecutive natural numbers. Now natural numbers basically would include anything, but consecutive means that they have to be next to each other. So just take 1 and 2. So if we do the sum of the squares of them, what do we get? We get 1 plus 4, and that gives us 5. Then let's try a different one. If you do 2 squared plus 3 squared, they have to be consecutive, you'll get 4 plus 6. Oh, I'm sorry, 4 plus 9, which is 13. You can see so far I've seen that the answer to both of those problems are odd. So my conjecture would probably be that if I added the squares of 2 consecutive natural numbers together, my answer would always be odd. And these are my examples. The last one here, where we're making a conjecture, is between the relationship between AB and EF. If it's saying that AB is equal to CD and CD is equal to EF, what is the relationship between AB and EF? And you could actually just describe this using the transitive property, and you could actually use that as your conjecture. So the transitive property, it basically means taking out the middle. So if you have a segment or anything that's equal to that same thing, you can take the first and the last terms and put them equal to each other. So we could basically do AB equals EF based on the transitive property. And then here we have a table. We're trying to think of what would be the best way to describe or display this data. This is talking about the postage stamps for the years 1982 through 2009. So I think the best way to display this data would probably be a line graph, where we would just plot points and then draw a line through it. So you might want to set up your graph. You obviously don't need all the quadrants, but you have the postage rates, and it goes by year. So years are always X because those are independent. And then the rate here is going to be your Y. So we go from 1982, and it looks like every 5 years. So you can do your same thing, 1982, 87, 92, 97, 2002, 2007, and 2009. And that would include all your years. Then we're going to have to label our y values. I would think maybe going by tens is fine. So we start at 0 always, and then 10, 20, 30, 40, 50. Could go up to 50, and then we're just going to plot the points. So 1982, 20, right here, 1987, 22. It's not very far up. 1992 is 29. Again, not much farther up from that. And then 32, again, we're not going up very far each time, so don't go too far on your graph. And then 37. 07 and 09. Okay, so yours is going to be a little bit more accurate just because it's a little bit tricky to do points on this, but you would, here's the points more obvious, and then you would connect the points with a line, and you could get a better idea of maybe the pattern. It looks like as the years go by, the rates are going to increase, and it looks like by about anywhere from 2 to 7 cents. So we could probably say that the next, over the next 4 years or so, or 5 years or so, that it's probably going to be past 50, or maybe right around 50. If we add up from about 44 cents, which is in 2009, and then 5 more years would be 2014, so the next year after that. So that's where I'm getting about 6 cents. So I would say maybe 49 cents. Oh, this is actually the next question. Predict the postage rate in 2015. So, excuse me, that's exactly what I went to say. So you're going to predict it like I was talking about, based on the pattern of the numbers. So we said about 49 cents. I would say anywhere between, I don't know, 46 to 50 cents would probably work. And then does it make sense that the pattern of the data will continue over time? I would say yes, because it looks like the postage has always continued to increase, even if it's just a little bit over time. So that's what I would do to explain myself. I'd say yes, and it's because there's a pattern, and I used inductive reasoning to make that pattern. And the last example is talking about a counterexample. So they'd give you a statement, a conjecture, and you need to basically prove that that conjecture is false based on giving me a counterexample. So this is saying that n is a real number, so negative n has to be a negative number. But if you think of a real number does include negatives. So if we had a negative value, like negative 3, that we put in for n, and then we're assuming that negative n is going to stay negative, well, if you're going to put in a negative 3, and the n is already considered negative, it actually ends up being positive 3, because you have a negative times a negative. Because right here, even though there's no number, that's considered a 1. So that would be maybe your counterexample, is just coming up with any negative number, plugging it in, and showing that when you do, it's not going to end up being a negative number. It's going to be positive. And then the last example, you have angles ABC is congruent to angles DBE, so that angle ABC and DBE we can assume, I guess, are vertical angles, but there's so many other angles that you could describe that are also congruent, and they don't always have to be vertical angles. So really just drawing two angles labeled correctly, like this, ABC maybe, and DBE. Just drawing them like this, where you have them labeled as being congruent, is also technically a counterexample, because that's not showing that they're vertical, but it is showing that they are congruent. And that concludes this lesson, lesson 2-1.